So today in this lecture, I'm gonna give an example of an uncountable set whose measure is 0. So in order to do that one, we are going to construct Cantor set, and then I'll be showing that Cantor set is a perfect set, and we are going to define what is a perfect set, and we are going to show that every non-empty perfect subset of R is uncountable. So in that way, we are able to show that Cantor set is uncountable, and then we will be showing that Cantor set has measure 0. So in that way, we are able to give an example of an uncountable set whose measure is 0. Right? So let us see what is a Cantor set. Cantor set. So it is one of the very important subset of R. So first we are going to consider a closed unit interval. So this is a closed unit interval, and then so it is denoted by C0. So it is denoted by C0. All right. So then so C0 is the closed unit interval 0, 1. Then from this closed unit interval, we are going to remove the middle third open interval. So we are going to remove this one. So the middle third open interval, it is named as I01, and that is exactly equal to 1/3 comma 2/3. So and it has length 1/3 also. The remaining set, this one also has 1/3. This one also length 1/3. The removed one is also 1/3. So the remaining set is a closed set, and it is denoted by C1. So it is the union of C11, that is closed interval 0, 1/3, and C12, that is closed interval 2/3, 1. Alright. So it is a disjoint union of two parts, C11 on the left, C12 on the right. Alright. So it is the first step of removing open interval. So that is why we name it C1 here, and it has two components, C11 on the left and C12 on the right. And this one has length 1/3, and this is also 1/3, and the removed one is also 1/3. So 1/3 you can write as 1/3 to power 1, because the first step of removing is 1. Therefore, in that way we can generalize. All right. And the next step, in the next step, it's second step, from the remaining part of C11, we remove the middle third open interval again. All right. So this is the C12 part of C1. From this one also we remove the middle third open interval. All right. So from C1 we remove the middle third open interval, and the removed interval's name is I11, and that is equal to 1/3 square comma 2/3 square, and it has length 1/3 square. All right. Similarly, from C12 we remove the middle third open interval I12, and that is exactly equal to 7/3 square comma 8/3 square, and it has length 1/3 square also. And the remaining part, this one also has 1/3 square length. This one also, this one also, this one also. So let us name this one, the remaining part, in this way: C21, C22, C23, C24. C2 means in the second step of removing open interval. All right, and all the union is called C2. Okay, so C21 is this interval, it has length 1/3 square. C22 is this interval, and C23 is this interval, and lastly C24 is this interval. All right. So the process continues infinitely. The process continues infinitely. So we have sequence of closed sets C0, C1, C2. C0 is the original one. C1 is the first step of removing open interval, and C2 is the second step of removing two open interval. Like that it goes on. So C0 is a closed interval of length 1, and then from C0 we remove the open interval I01, that is 1/3, 2/3 of length 1/3, to get the closed set C1. The joint union of two closed intervals C11, C12, is of length 1/3. Okay. So from C1 again, C1, we have already shown that C1 has two components, C11 on the left, C12 on the right. So from C1 we remove the open interval I11, that is 1 by 3 square comma 2 by 3 square, and 1 by I12, that is 7 by 3 square comma 8 by 3 square, each of length 1 by 3 square, to get the closed set C2. A disjoint union of four closed intervals C21, C22, C23, C24 that we have already shown, by picture, and is of length 1 by 3 square. Alright. So thus for a non-negative integer n, we get a closed set Cn. So just like we got C1, C2, for any non-negative integer n, we will get Cn, and the construction is similar. So, and what is Cn? Cn is a disjoint union of 2 to the power n closed interval, namely C and k running from 1 to 2 to the power n, each of length 1 by 3 to the power n, formed by removing the middle third interval in minus 1 r going from 1 to 2 to the power n minus 1 from the previous step Cn minus 1. Okay, that is how we get Cn. From the previous step Cn minus 1, we remove the open third, middle open third, middle open intervals. Okay, so each interval in minus 1 r is of length 1 upon 3 to the power n, that we have already shown it. Okay, so then we can write Cn is equal to union, disjoint union. This is a disjoint union. How many interval? 2 to the power n, k running from 1 to 2 to the power n, Cnk. Okay, for a fixed step, 100 step n is fixed, but k running from 1 to 2 to the power 100, like that. Okay, so that is how we get Cn. And then you put C is equal to intersection n going from 0 to infinity Cn. Then C is a closed set, because if Cn is a closed set, therefore their intersection will be also a closed set. So this C is called a Cantor set. That is how we form Cantor set. Okay, so Cantor set is intersection n going from 0 to infinity Cn. Alright, so what is the complement of Cantor set? So how you got Cantor set? So you get Cantor set by removing intervals. Okay, in each step you remove intervals, so the remaining set, the remaining set is called a Cantor set. Okay, so then the complement of the Cantor set will be those intervals that have been removed. So the complement of Cantor set, that is 0, 1 closed interval differential, is equal to the union of all the interval you remove. Okay, so this is the interval you remove in each step. Okay, so if you take union from n going from 1 to infinity, this whole union will give you the total number, every interval that you remove in each step. Okay, that is the complement of Cantor set. Alright, so what is the thing you have to remember? The complement of Cantor set is disjoint union of removed interval. Alright, so every interval is measurable, so it is a disjoint union of measurable set. So therefore measure of complement of Cantor set is equal to sum n going from 1 to infinity, measure of the union of the interval in the nth step. So this is the union of the interval in the nth step, its measure. Okay, so how many interval you remove? 2 to the power n minus 1 interval you remove, is of length 1 upon 3 to the power n. Okay, so if you sum up all those interval in the nth step, that you will get 2 to the power n minus 1 divided by 3 to the power n, and summation n going from 1 to infinity, and that is a geometric series, and it has sum equal to 1. Alright, so what does it say? It says that the measure of the complement of the Cantor set is equal to 1. Okay, but the 0, 1 closed interval can be written in this form: complement of Cantor set union C, and this is a disjoint union. Alright, but measure of the interval is equal to 1, measure of this one is equal to measure of the complement C plus measure of C. Okay, but measure of this one is 1, and now we have shown that measure of complement of C is equal to 1. So ultimately what you get, measure of the Cantor set is equal to 0. So now we are able to construct Cantor set, and now we are able also to prove that Cantor set has measure 0. So if we are able to show that Cantor set is uncountable, then it is done. That is, we are able to give an example of an uncountable set whose measure is 0. All right. So next we are going to show that the Cantor set is perfect set. Okay. So if Cn is a closed set, all right, Cn is a subset of Cn minus 1 and Cn is closed set for each n. If Cn is formed by removing the middle third components of the constituent closed interval Cnk. All right. So Cnk, how many such components are there? Cnk of Cn. All right. So Cn has component Cnk, k running from 1 to 2 to 4 n. So from each component you have to remove the middle third open interval, and then you will get the next step, next Cn. All right. So therefore points in 0, 1 which have never been removed in the process are precisely the points of the Cantor set C. So how you form Cantor set? You are removing the open intervals. So you are removing points. So in each step, if you don't remove a point, those points will be precisely the points in the Cantor set. Okay. So we see that point 0, 1. So 0, 1 is the end point of C0. So when you remove the middle open third interval, 0, 1 is always there. I mean 0, 1 have never been removed. So it's likewise 0, 1 by 3, 2 by 3, 1 of C1, etc. have never been removed. In general, k divided by 3 to the power n, where k is greater than or equal to 0, less than or equal to 3 to the power n, are endpoints of the constituent intervals. Okay, and they have never been removed in the process. In any process, okay, this point like this k divided by 3 to the power n have never been removed. So they are precisely points in Cantor set. So points k divided by 3 to the power n, where k lies between 0 and 3 to the power n, for n greater than or equal to 0, are points of Cantor set C. So a subset of R is said to be perfect set if it is closed and every point is a limit point of itself. So let us first define the perfect set. Perfect set is a closed subset of R, and every point of it is a limit point of itself. Then we said that that set is a perfect set. Okay. So some example, 1, 2 interval, it is not a perfect set because this set is not a closed set. All right. So next, minus 2, 7, 9, it is a closed set, but it is not a perfect set because none of these point is a limit point of itself. All right. So in another word, every point of this set is not a limit point of itself. Okay. So closed interval 1, 2 is a perfect set because it is a closed set and every point of this set is a limit point of itself. All right. So every finite set is a closed set, but it is not perfect. Every closed and bounded interval is a perfect set. So this is some example of perfect set. So Cantor set is a perfect set. Now let us prove that Cantor set is a perfect set. So what we have to do, you take a point from the Cantor set, and then we are going to show that that point is a limit point of the Cantor set itself. Okay. In another word, we should be able to find a sequence of points in the Cantor set whose that is converging to that point. So that is what we are going to use here. We know that Cn is equal to disjoint union of interval Cnk, k running from 1 to 2 to the power n. Is a disjoint union of 2n closed, 2 to the power n closed interval, and is of length 1 upon 3 to the power n. So, and then we form the Cantor set in this way. Cantor set is equal to intersection n going from 0 to infinity Cn, and therefore Cantor set is a closed set. Okay. So the remaining thing that we are going to prove is that the Cantor set is every point of Cantor set is a limit point. Then Cantor set will be a perfect set. So for that, let us take an arbitrary point x from C. Okay. And then since C is formed by intersection of this form, x belongs to C means x is a member of every Cn. Okay. So x belongs to Cn for all n greater than or equal to 0. So that means x also is a member of C1, implies that how many C1 has two components. Okay. X belongs to one of the disjoint closed interval. C1 is disjoint closed interval C1 and C1 2. Alright. X belongs to C1 means x is either here or here, and this one has length 1 by 3. Okay. So without loss of generality, we can suppose that x belongs to C1 1, and then in the next step C2 and intersection C1 1. So C2 and intersection C11, it is a disjoint union of two interval. So consists of two closed interval, one of which contain X. So X, because X is a member of C2 also, X is a member of C11 also, and therefore X belongs to C2 intersection C11, but C2 intersection C11 consists of two disjoint closed intervals. Okay, so X should be member of the one of the disjoint closed interval. So, and then take X1 to be an endpoint of the closed interval. That means this X belongs to C2 intersection C11, but C2 intersection C11 is a disjoint union of two closed interval. Then X should be member of the one of the interval. Alright, and then you take X1 an endpoint from other interval where X is not a member. Okay, so take X1 to be an endpoint of the other closed interval. So X is not equal to X1. Alright, next, since X1 is a member of C11, but the length of C11 is 1 upon 3. Therefore, distance between X and X1 should be less than or equal to 1 upon 3. So this is true. And next, X is a member of C2 also, and C2 is a disjoint union of 4 closed interval like this. We have already shown that one. Each of length 1 upon 3 square. The point X is one of the closed interval. Okay, is in one of the closed interval. So X is either here, either here, either here, either here. Okay, so without loss of generality, okay, so we can assume that X is member here, C2. Alright, so because X will be either here or here, so we can assume that X is here. Alright, so then again C3 intersection C22 is also a disjoint union of two closed intervals. Okay, since X is a member here, X should be either in one of the closed disjoint interval. Alright, so take X2 to be an endpoint of the other interval. So X belongs to one of the interval, and then you take another point X2, that is the endpoint of the other interval. Okay, that way X is not equal to X2. Okay, so since X and X2 is in C2 and the length of C2 is 1 by 3 square, therefore X minus X2 is less than or equal to 1 upon 3 square. So the process continue infinitely. Continuing in this way, we construct a sequence Xn. Okay, in C, so every member of this sequence is in C, the Cantor set. So, and by our construction, X is never equal to Xn for all n greater than or equal to 1, and distance between X and Xn is less than or equal to 1 upon 3 to the power n. Then as n tends to infinity, then Xn tends to X. So limit n tends to infinity, Xn is exactly equal to X. So what we get, we take a point from the Cantor set, that is point X, and then we are able to construct a sequence in the Cantor set. That sequence is converging to that point X. Therefore, this point X is a limit point of the Cantor set C. But the point X was chosen arbitrarily from C. Therefore, what we conclude is that Cantor set, every point of Cantor set is a limit point of itself. Therefore, Cantor set is a perfect set. Hence, C is a perfect set. Alright. So next, now we are able to prove that Cantor set is a perfect set. Next, we are going to show that every non-empty perfect subset of R is uncountable. That way, Cantor set will be also uncountable. Alright. So every non-empty perfect subset of R is uncountable. Okay. So let E be a non-empty perfect subset of R. Alright. So if possible, we assume that E is countable. We are assuming that E is countable. That is by method of contradiction we are going to prove. Alright. Since E is countable, E may be enumerated as a sequence. Okay. The element of E can be enumerated as a sequence x1, x2, x3 like that. Okay. So we construct a sequence Yn. From this sequence or from the set E, we are going to construct another new sequence Yn inductively as follows. Okay. So the first element of the sequence y1 is equal to x1, and the second element y2 is equal to x2, and then let us try to find out the third element in the following way. Okay, so we can take a small number epsilon 1 that is less than x1 minus x2. Okay, x1 and x2 are 2 points, and that they are equal to y1 and y2. There are different points. Their difference will be a real number. Modulus will be a positive real number. From that real number, we can take a small number which is less than from that real number. Okay, so that is quite possible. That way, x2 is the center and epsilon 1 is the radius, and then this open ball, orange open ball, will not contain x1. Alright, because epsilon 1 is less than distance between x1 and x2. So this open ball will not contain x1. Alright, so it is an open neighborhood of x2, but x2 is a point in E, but E is a perfect set, so x2 will be a limit point of E. So this open neighborhood will contain some other member of E. Alright, some other member of E. So that member, you can take some member y3, let us name it y3, the third element of the sequence. Okay, so it will be here, somewhere here, some member of E that is coming from the definition of perfect set. Since E is a perfect set, any neighborhood of x2 will contain some other point of E, and that you can take arbitrarily one point. Let us name that one y3, that is the third element of the sequence. Okay, so open neighborhood bx2 epsilon 1. All right, so we can take y3 so that y3 is not equal to x3. So when you take y3, you deliberately take y3 not equal to x3. And then next, again, we take epsilon 2 such that ball center at y3 and radius epsilon 2 is a subset of ball center at x2 radius epsilon 1. Alright, so then you take epsilon 2 deliberately in such a way that it is less than epsilon 1 by 2. Further, you can make epsilon 2 sufficiently small so that x1, x2, x3, they are not in this ball. Alright, so see, you take epsilon 2 sufficiently small so that this open ball center at y3 radius epsilon 2 does not contain x1, x2 and x3. Alright, so this process continue. So by perfectness, we can find again y4, that is an element of E. So y4 also belong to this open ball. Alright, so we take epsilon 3 such that the open ball by epsilon 3 is a subset of ball y3 epsilon 2. So, and then epsilon 3 is less than epsilon 2 by 2. Further, we make epsilon 3 sufficiently small so that x1, x2, x3, x4, they are not member of by4 epsilon 3. Alright, so by induction, we have constructed the sequence yn such that the first ball is a superset of second ball, and the second ball is a superset of third ball, like that. So we have constructed sequence of ball. The center of the ball is a member of the sequence. Alright, so and then x1, x2, xn does not belong to the ball at the nth step byn epsilon n minus 1 for all n greater than or equal to 3. It is obvious that epsilon n is less than or equal to epsilon 1 by 2 to the power n minus 1 for all n greater than or equal to 1. So for a given epsilon, there exists a positive integer n such that, epsilon 1 divided by 2 to the power n minus 1 is less than epsilon for all n greater than or equal to capital N. Let n and m be such that mn greater than or equal to capital N. If m is greater than or equal to capital N, what we have, ball centered at yn epsilon minus radius epsilon n minus 1 will be a superset of ball centered at ym radius epsilon m minus 1. So yn and ym, they are member of balls centered at yn radius epsilon n minus 1. So therefore, a distance between yn and ym should be less than epsilon n minus 1. But epsilon n minus 1 is less than epsilon 1 by 2 to the power n minus 1. But this one is again less than epsilon. And this is true for all mn greater than or equal to capital N. It shows that the sequence is a Cauchy sequence, and it is a Cauchy sequence in E. E being perfect, this Cauchy sequence should converge to some point y0. So then, indeed, y0 should be a member of every open ball for all n greater than or equal to 2. And since x1, x2 up to xn, they are not member of this ball for all n greater than or equal to 3. So y0 cannot be equal to xn, because y0 is here and x1, x2 up to xn, they are not here. So xn cannot be equal to y0 for all n greater than or equal to 1. So what does it say? It says that, y0 is a member of E, but y0 is not equal to xn. Since E is countable, we assume that E is countable, so every member of E can be some xn. So but y0 is not equal to some for all y0 is not equal to xn for all n. So that means we are arriving to a contradiction. So that contradiction is from our assumption that E is a countable set. So there no such enumeration exists for E. So therefore E is uncountable. E is uncountable. That means every non-empty perfect subset of R is uncountable.